Bhargava factorial. In mathematics, Bhargava's factorial function, or simply Bhargava factorial, is a certain generalization of the factorial function developed by the Fields Medal-winning mathematician Manjul Bhargava as part of his thesis in Harvard University in 1996. The Bhargava factorial has the property that many number-theoretic results involving the ordinary factorials remain true even when the factorials are replaced by the Bhargava factorials. Using an arbitrary infinite subset S of the set C of integers, Bhargava associated a positive integer with every positive integer k, which he denoted by k s with the property that if one takes s equals z itself, then the integer associated with k, that is k, c, would turn out to be the ordinary factorial of k. Motivation for the generalization. The generalization. Example: factorials using set of prime numbers. Let S be the set of all prime numbers p equals 2, 3, 5, 7, 11. 11, 11, 11, 11, 11. Choose p equals 2 and form a p ordering of p. Choose A0 equals 19 arbitrarily from p. To choose A1, the highest power of p that divides 2 A0 equals 17 is 20 is 20 is 20 is 20 is 20 equals 1. Also, for any a, 2 and p A0 is divisible by 2. Hence, the highest power of p that divides A1 A0 is minimum when A1 equals 2, and the minimum power is power is minimum power is 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 1. Thus A1 is chosen as 2 and VO P2 equals 1. To choose at WO, it can be seen that for each element and in P, the product x equals A0 A1 equals a 19 a 2 is divisible by, visible 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 by, visible. 2. Also, when a equals 5, x is divisible 2, and it is not divisible by any higher power of 2. So A2 may be chosen as 5. We have V2P2 equals 2. To choose A3, it can be seen that for each element and in P, the product x equals A0 A A2 equals a 19 a 2 of 5 is divisible by 23 equals 8. Also, when A equals 17, x is divisible by 8 and it is not divisible by any higher power of or of 2. Choose A3 equals 17. Also, we have V3P2 equals 8. To choose a fur, it can be seen that for each element in P, the product x equals A0 A A2 A3 equals a 19 a 2 of 5 is 17 is divisible by 24 equals 16. Also, when A equals 23, x is divisible 16 and it is not divisible by any higher power of 2. Choose a fur equals 23. Also, we have V4P2 equals 16. To choose a fiv, it can be seen that for each element in P, the product x equals A0 A A2 A3 a fur equals a 19 a 2 of 5 is 17 a 23 is divisible by 27 equals 128. Also, when A equals 31, x is divisible 128 and it is not divisible by any higher power of 2. Choose a fiv equals 31. Also, we have V5P2 equals 128. The process is continued. Thus, a 2 ordering of P is 19, 2, 5, 17, 23, 31. And the associated 2 sequence is 1, 1, 2, 8, 16, 128. Assuming that V0P2 equals 1, for P equals 3, one possible P ordering of P is the sequence 2, 3, 7, 5, 13, 17, 19. and the associated p sequence of p is 1, 1, 1, 3, 3, 9. For p equals 5, one possible p ordering of p is the sequence 2, 3, 5, 19, 11, 7, 13. And the associated p sequence is 1, 1, 1, 1, 1, 5. It can be shown that for p equals 7, the first few elements of the associated p sequences are 1, 1, 1, 1, 1, 1. The first few factorials associated with the set of prime numbers are obtained as follows: sequence of 53,657 in the OAs. Table of values of vk, p, and k. P. Example: factorials using the set of natural numbers. Let S be the set of natural numbers z. For p equals 2, the associated p sequence is 1, 1, 2, 2, 8, 8, 16, 16, 128, 128, 256, 256. For p equals 3, the associated p sequence is 1, 1, 1, 3, 3, 3, 9, 9, 9, 27, 27, 27, 81, 81, 81. For p equals 5, the associated p sequence is 1, 1, 1, 1, 1, 5, 5, 5, 5, 5, 25, 25, 25, 25, 25. For p equals 7, the associated p sequence is 1, 1, 1, 1, 1, 1, 1, 7, 7, 7, 7, 7, 7, 7. Ah, ah, um, 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 and so on. Thus, the first few factorials using the natural numbers are 0, z equals 1 xon x equals 1, 1, z equals 1 xon x equals 1, 2, z equals 2 xon x equals 2, 3, z equals 2 3 xon x equals 6, 4, z equals x3 xon x equals 24, 5, z equals x3 xon x equals 120, 6, z equals 16 xon x equals 720. Examples: some general expressions. The following table contains the general expressions for k, S for some special cases of S. Properties: